Question from communication system, where the concept of product modulator is used, and we have to determine what is the microsampling frequency of the signal YT. Okay, so let us see this. X1T and X2T are two bandwidth signals having bandwidth 4 pi 10 to the power 3 radians per second each. In the figure, this figure which is given here, so X1T and X2T is getting multiplied with cos 4 pi 10 to the 3t, cos 12 pi 10 to the 3t. They are getting added together and we are getting YT. So we have to find the sampling rate for YT, the Nyquist sampling frequency of YT. So we need to determine what is the maximum frequency present in YT, and twice of that is going to give me the Nyquist sampling frequency. Okay. So I can write YT is X1T cos 4 pi 10 to the power 3t plus X2T cos 4 pi 3t. So the maximum frequency of this and this will help you to find out the maximum frequency predicted. So we know that when you multiply any signal with cosine function, the spectrum gets shifted by that. Okay. So let's assume that X1T has got the spectrum X1 of X, and let's say it is something like this. Okay, so this is 4 pi into 10 to the power 3 minus 4 pi into 10 to the power 3. So once you multiply this, you will get the spectrum of this signal, maximum frequency present in X1T cos 4 pi 10 to the power 3t. The spectrum will be like this. This will get shifted by 4 pi. So it will become 8 pi into 10 to the power 9, and this is it. Of course, this side will also be there. We are not worried about it. We need to find out the maximum frequency. Similarly, X2T cos 12 pi 10 to the power 3t will have a spectrum like this. This whole spectrum, let's say the spectrum of X2T is something like this. F. Forget about F for omega, they are the simplification. Something like this. Minus 4 pi 10 to the power 3. 4 pi 10 to the power 3. So once you shift it, shift by 12 pi. So 12 pi central. This will be 12 pi plus. So this will become around 16 pi 10 to the power 3. Because 8 pi 10 to the Now, when you add X1T and X1T cos 4 pi t and X2T cos 12 pi 10 to the 3, the maximum frequency present in this is 16 pi 10 to the power 3. Okay, so the max frequency present in pi t is 16 pi 10 to the power 3. Okay. Radians per second. So the Nyquist sampling frequency Fs is going to be 2 into 16 pi in this power 3, that is 32 pi into 10 to the power radians. Sample per second, so that will be the 32 pi into 10 to the power 3. So the concept used here is the shifting in the frequency domain and the maximum frequency when two signals are added. Okay, so when two signals are added, the maximum frequency present in the output signal is nothing but the maximum of the two signals which are added, maximum frequency of the two signals which are added. The answer for this is 32 pi 10 to the power 3, option D. That's the end of question for communication system. Okay, let's see this question from communication system. It is from the analog communication portion of the syllabus. Let a frequency modulated FM signal right, which is given by this equation. The MT is a message signal of bandwidth W. It is passed through a nonlinear system with output yt is equal to 2xt plus 5xt square. Let Bt denotes the FM signal bandwidth. The minimum value of omega c required to recover xt from yt is how much? Now, directly in this, the bandwidth of the FM signal is given. That means the bandwidth of xt is given. Okay, so and that is nothing but Bt. The bandwidth xt is equal to Bt, right? Now, when this xt passed through a nonlinear system, here output yt is xt plus 5x squared t. Now, when an FM signal passes through a nonlinear device or nonlinear system, what happens to the bandwidth? What happens to the frequency? They just get multiplied by a factor of nonlinearity, in the order of nonlinearity, right? So here, what will happen? Your omega c will get double. Your bandwidth the Bt will have changed. The message signal bandwidth remains unchanged. Frequency deviation will also become double. Okay, we need not to worry about the frequency deviation and other things because that is not given directly. Bandwidth Bt is given, right? So if I see the spectrum of an xt, the spectrum of xt will look something like this. Outside the spectrum right now. Heavy component. And the remaining side looks FM signal spectrum contains many number of side lobes. They are not fixed depending on the number of side lobes here. So I'll just write it. This is omega c, right? And these are the side lobes. You can set as the delta values. Okay. Omega c plus omega m, omega c plus 2 omega m, omega c plus n omega m. Where omega m is nothing but the message. So we need not to worry about it in this comment. Let's give it this omega radius. Perfect. Yeah. Now what will happen? Just make it simpler. If I take this bandwidth up to this point, so this is omega c plus bt by 2, and this is omega c minus bt by 2. So assume that up from here to here the spectrum of FM signal like this. Now when this spectrum passes through a nonlinear system, what happens to the spectrum? Let's see that. Now the output the nonlinear system will have a spectrum like this. So this will be present with every component. And once it passes through a nonlinear system, it will have 2xt component also, 2 omega c. So there will be some 2 omega c component. This is omega c. This is omega c. This is coming because of x squared t terms. Okay, because of this term. And this is coming because of x theta. Right? Now this has got a spectrum from, I'll mark here, omega c plus bt by 2, omega c minus bt by 2. Okay, let's assume spectrum is here. 2 omega c plus bt by 2. This will also have a spectrum which is spread, right? Because delta f will be more here. Okay, so this will become 2 omega c plus bt because bandwidth will become double after passing through this. And this is 2 omega c minus bt. Now, if I want to get only this portion, right, then this portion should be completely isolated. That means here I must get 2 omega c minus bt, right? Must be greater than omega c plus bt by 2, right? So this gives me condition omega c must be greater than p bt by 2. So that is the answer. And the massive signal bandwidth will become double in this case. X square t will have bandwidth 2 bt. Xt has got the bandwidth bt. Same thing has come over here. And to get this portion alone, 2 omega c minus bt. That means this should be greater than omega c plus bt by 2. So you can recover this and you can discard. Okay. So to recover this, omega c must be greater than t bt by 2. 3 by 2 bt. So that is the concept in this. So the important thing that we need to remember while solving this problem is that the nonlinear functions, the nonlinearities will increase the carrier frequency, also increase the bandwidth. Now, whatever is the order of nonlinearity, the carrier frequency and the bandwidth will get multiplied by that order. Okay. Exactly. I think the bandwidth need not multiply, but yes, in this case we can say so because we do not know what is delta F. Otherwise, we can determine delta F also because massive signal bandwidth W is given, BT is given. So BT is 2 times omega c, sorry, delta F plus W. Okay. So delta F is going to be BT by 2 minus W. So here in this case, delta F will become multiplied by 2. So this will become, again it will come to the same thing because delta F is difficult to find from this, right? At the end, we will conclude that this is the answer for this is P by 2. That's the end of question for communication system. Let's see this question from communication system. From the random process part, the transition of a wide sense stationary random process to an LTI system. So Xt be a wide Gaussian noise with pass field density 1 by 2 W per Hertz. Xt is input to an LTI system with impulse response e to the power minus TUT. The average power of the system output is we have to find. So it is something like this, that you have an LTI system. Input is, let's say, output is impulse response Ht. Frequency response is H of. Okay. Now I know by the principle that Sx, Sy of f is H of f magnitude square Sx of f. Okay, because it is given in hertz, so we'll write in terms of frequency only, right? And if I want to find the output power, it is integral minus infinity to infinity Sy of f dx. I can substitute this thing here, it will become minus infinity to infinity H of f into the square Sx of f dx. Sx of f is given by 2 watts per hertz. So you can write output power equal to, it is nothing but the area under the pass field density, right? So this is the relationship of the pass field densities. And then output power here is going to be, Sx of f is 1 by 2, so I can write 1 by 2 outside, minus infinity to infinity H of f into the square dx. Now one principle is there which says that Parseval's figure, right? It says that using Parseval's theorem, minus infinity to infinity xp minus square dt is minus infinity to infinity half f y dx. Right. So I can replace this with ht e to the power minus t ut square. So this will become by t minus infinity. Now minus infinity to infinity, uh, h of t minus t square dt will become 1 by t 0 to infinity e to the power minus t whole square, that will become minus 2t dt. And this when you solve, you will get, well, this 1 by 4 is nothing but 0.25. The answer for this is 0.25. Round up to the decimal. Okay, simple question. Only thing is we need to know this one. This is known and we can find it. And the area under the particle density is the total, gives me the total output power. And finally the Parseval theorem. So three important concepts. First is this, right? Second thing is the area under the PSD, which is equal to the output power. And third one is using the Parseval. It will be difficult if you start finding it, then you start solving it to integral e to the power minus tut frequency transformation 1 upon 1 plus omega square, right? A plus omega, a square plus omega. That becomes difficult. So instead of that, if we make use of Parseval theorem, we can see this. So the answer for this is 0.25. That's the end of question from communication system. Question from communication system. This is a 1 mark question, and yes, there could be a chance that could be multiple options may be correct in this. So let's see what is the question. For a real signal, which of the following are valid power spectral densities? Okay, so you can see here multiple options can be correct. Okay, so let's see that how to find out the valid power spectral densities. The power spectral densities have got a certain properties, right? For a real signal, the power spectral density is real and symmetric. It is always real. Power spectral density is never a complex quantity. It is always real. Okay, so the first property is for real signal, power spectral density is always real and even. That's it. This property itself will give you the idea that what is going to be the answer. Now I see this is a real and even function, right? So this is the right answer. This is also a real and even function because with respect to omega, fx of omega as fx of minus omega are same. This is also the right answer. This is real, but it is odd in nature. This cannot be the right answer. And it is becoming negative also. You see, power spectral density is always a positive one. Second, we can take that fx of omega is always greater than equal to 0. This is also not the right answer because it is real, it is positive, but it is not an even function. It is only one-sided. So this could be true for a complex signal, but not for a real signal. Okay. So the correct answer for this is option A and option B. Okay. That's the end of question from communication system. Question from communication system. This is from the random variable and that part of the syllabus. And here, it may be appear that this may be a little tough question, but yes, it is not so because the options are made simpler in this. Okay, so we will see. And in this, I'm sure that only one option will be the right. The random variable x distributed normally as normal distribution with zero mean and standard deviation 1 undergoes the transformation y equal to hx as it is shown in the figure. Okay. The form of the probability density function of y is x. So the form is asked. It is not asked what is the probability density function of y. Okay, so that's where the question is easier. If someone asks what is the probability density function, then it becomes a little tighter, but we need not to worry about that. Okay, so what we have to see here is, let's start. So here, The random variable x, since it is normally distributed, so I can write fx of x something like this. Okay. So mean equal to 0, variance equal to 1. We need not to worry much about it, right? We have to see about it, this function y equal to x. Now, if you look at the function closely, so here I can write minus 1, 1, 2, minus 2. Okay, this is like that. This x of x. This is only just to see the boundary. Now, by looking at this function, you can say clearly that though the random variable x is continuous random variable, but random variable y is not a continuous random variable. It is a combination of discrete as well as continuous random variable. Okay, so if you look at y and if you try to form an equation, try to get what it is. So y is equal to 1 when x is greater than 2, right? And y is equal to minus 1 when x is lesser than minus 2. And similarly, y is equal to 0 when x is lying between minus 1 to plus 1, right? Quality sign, you need not to worry much about it. So y is having three discrete values, 1, minus 1 and 0. You can see from the graph 1, 0 and minus 1. These three discrete values are there. So these three discrete part of the random variable. But whereas if you look at closely this equation of line, y is equal to x plus 1 for all x greater than 1 less than 2. Okay. So when it is x is lying between 2 and 1, you can see clearly that it is nothing but equation of this line, which is x plus 1. Okay. Similarly, in this case, it is going to be minus x only, x minus 1. Sorry, I think it should be x minus 1 here. It should be x minus 1. It will become x plus 1 or x lying between minus 2 and minus 1. Okay. So that's how this. So this will give the continuous random variable part. Continuous random variable part, and this is discrete random variable part. Okay. So you must be knowing that the discrete random variables are represented. The probability density functions are represented using an impulse function. Okay. So where those impulses occur? The impulses will occur where the discrete random variable is taking the values. So one impulse will occur at 0. One impulse will occur at 1, other impulse will occur at minus 1. So I have something like delta of y is equal to 0 plus delta of y minus 1, right, plus delta of y plus 1. So this is corresponding to y equal to 1, this corresponding to y equal to minus 1, this corresponding to y equal to 0. So three impulses are there. Okay. Plus some continuous function which is representing this continuous random variable. So that could be, if you see here, that could be, let's say it is g, y. We need to worry about this. We need to worry about the forms. And these constants, of course, we can find, but here a, b, c are given. So the form here is you can represent this as a, you can write this as a, you can write this as b, you can write this as c. Of course, a, b, c values are not required to be found. Okay. So the correct answer for this will become option B. So the form of the random variable y will be of this form. That is what is required. Someone asks what is a, b and c value. Then it is easy to find because a is for x greater than 2. So y equal to 1, I'll take one example. Y equal to 1 is implies, here let me just probability of y equal to 1 is same as probability of x greater than 2, and that is nothing but equal to q function of 2, right? So probability of y equal to -1 is also same because this and this are same, right? So that is also become q of 2. And probability of y equal to 0 is q of -1 because we have to find out this region, right? The area of this region is q of -1 minus q of 1. Okay, so that is the answer. So ABC values can be obtained from this, right? These denote nothing but the probabilities. And remaining continuous random variable part is denoted by P of y. So correct answer for this is option D. That's the end of question from communication system random variable part. This is a question from communication system information theory part. Yes. So let us read this question. Directly, if you read it, may appear as a question of aptitude or general aptitude part, but yes, in communication, the information theory is something like where the general aptitude falls upon, right? So it is nothing but simple. The frequency of occurrence of 8 symbols is shown in table. Okay, so A, B, C, D, E, F, G, H. At what frequency they are occurring? A symbol is chosen and determined by asking a series of yes no questions which are given to successfully answer. The average number of questions and asked in the most efficient sequence to determine the chosen symbol is. Actually, it is indirectly it is asking the minimum number of bits required to encode the given source. Now source is containing 8 symbols. Symbols probabilities are given. That means you have to find out nothing but the entropy. Okay. So the most efficient way of source encoding is entropy. So the entropy of the source will give me that answer. So I can write simple h of s as the probability of occurrence of symbol A into log 2 of 1 over probability of symbol E. So I can write this as 1 by 2 log 2 of 2 plus 1 by 4 log 2 of 4 plus 1 by 8 log 2 of 8 plus 1 by 15 log 2 of 15 plus 1 by 15 log 2 of 2 plus 1 by 54 log 2 of 54 plus 2 times 1 by 20 1 by 22 times 2 times 1 by 28 log 2 log 20. So now I can simplify this 1 by 2 4 divided plus 4 plus 2 plus 32 plus 54 plus 13 by 128. You can further simplify this. Take this here 28 54 plus 54 54 plus also 54 and there is 2 times plus 32. You can just correct it. What we get 8 32 and plus is all good. Let's see what is the result. So the average number of questions in this case is going to be 2 questions. Okay. The answer for this is 2 questions. See, number of questions will be always an integer number. So rounded off to 2 decimal places doesn't have any purpose here. If you just add 2 also, that is also correct. Please check the calculation once. So answer for this is 2. The 2 questions can be asked, whose answer is yes or no. That's the end of question for communication.